Hello students, welcome back to second topic of first unit. Here we are going to discuss the static and dynamic characteristics, that is characteristics of sensors. So far we have seen the first topic, overview of sensors and classification. Now we will complete static and dynamic characteristics, and these are the remaining topics in unit number 1. So, static characteristics are listed here. The first one is range and span, error, accuracy, precision, sensitivity, hysteresis error, nonlinearity error, repeatability. It is also called as reproducibility, stability, drift, deadband resolution, output impedance, threshold. And the dynamic characteristics are six: response time, time constant, rise time, settling time, and fidelity. So these characteristics we are going to discuss elaborately in our session today. Fidelity and lag, we have one more characteristic. So totally six characteristics. So static characteristics are after reaching the steady state condition by any measurement, then the characteristics exhibited by the sensor are known as static characteristics. Here, the static characteristics are the values given when steady state conditions occur, i.e., the value, that is the values given when the transducer has settled down after having received some input. So after settling down to some steady state condition, the characteristics are studied here. In dynamic characteristics, it is the behavior between the time that the input value changes and the time that the value given by the transducer settles down to steady state value. So before settling down to steady state condition, the behavior exhibited by sensor or measuring device are known as the dynamic characteristics. So behavior and its characteristics. So next we have dynamic characteristics. There are inputs to the system. There are actually five inputs. We will see them in today's session itself. First, we'll complete the static characteristics. The first one is range and span. It defines the limits within which the input can vary. So here range is from the minimum value to maximum value. So two values you have to specify here in order to mention the range of any measurement device. The span is the maximum value of the input minus minimum value. So maximum minus minimum, you will be getting one value. So it is a single number, whereas range you need two numbers. So from two both numbers should be specified. And we have the load cell for the measurement of force have a range of 0 to 50 kilonewton. So the span is maximum minus minimum, that is 50 minus 0 is 50 kilonewton. So here error is the difference between the result of measurement and the true value of the quantity being measured. So here actually the error is measured value minus true value, measured value minus true value. So it can exist in both, in terms of positive, in terms of negative. So accuracy is the extent to which the value indicated by a measurement system might be wrong. So this is the way it is defined: the summation of all possible errors that are likely to occur, as well as accuracy to which the transducer has been calibrated. Here, this accuracy is mentioned in terms of plus or minus values. It is plus or minus 2 degrees centigrade. It means that the measurement value may lie between minus 2 to plus 2 values. So it can vary. It can lie within that range. So here accuracy is normally expressed as a percentage of full range output, full scale deflection. Here plus or minus 5 percentage of full range output. It means that 0 to 200 degree centigrade, right? If it is plus or minus 5 percentage, so 200 degree the percentage, 5 percentage of 200 will be 10 degree centigrade, plus or minus 10 degree centigrade of the true reading. So that is the accuracy of this particular instrument. Next we have precision. It is the equipment which is precise is not necessarily accurate. So here the precision is defined as the capability of an instrument to show the same reading when used each time. So reproducibility of that instrument is good. So this diagram we can see, this is the target. So here all the arrows are meeting at the target value. So accuracy is good as well as precision is good. So here the you can see here it is not concentrated on target, but all arrows are nearer, right? All arrows are meeting here. So precision is good but accuracy is poor, whereas here it is staggered. It is not it is neither accurate nor precise. So this is the precision. Next we have sensitivity is the relationship indicating how much output there is per unit input. So output by input relation is known as sensitivity. Minimum input of physical parameter that will create a detectable output change. So here the resistance thermometer may have a sensitivity of zero point 0.5 ohms per degree centigrade, indicates the sensitivity to inputs other than that measured. So that may be due to environmental changes. A transducer for the measurement of pressure is having a temperature sensitivity of plus or minus zero point 0.1 degree per percentage of the reading per degree centigrade change in temperature. So this is the example for sensitivity. So it is normally detectable output change. So that is per input, whatever input you are giving, the detectable change is known as sensitivity. So sensitivity, and we have one more term, resolution. So here this step, you have steps, right, from for input to output. So this step is step slope is now indicating this sensitivity, whereas a resolution is observable change. The input, the minimum input that produces the observable change is known as resolution. So that is obviously step width. Step width is becoming resolution here. So that is the minor difference between sensitivity and resolution. We have hysteresis error. It is also known as loading error. It is increasing here while loading, and it is not following the same path while unloading. So that is hysteresis, and the difference between these two curves is the hysteresis error. It is a type of error only. Next, we have nonlinearity error. So this is the nonlinearity error for end range values. So this is the linear curve, and this is the actual measured curve. So the difference between these two is becoming error, and here the nonlinearity is measured from end range values, from end range values. So we have this is the upper limit and this is the lower limit, and linear curve is drawn between end range values. So this is one way to predict nonlinearity. Another way is we have This is non-linearity error using best straight line for all values. So this is the best straight line drawn. This is the linear curve drawn, the best straight line for all values. So it is done by method of least squares. Method of least squares. And we have the best straight line through 0 point. This is the best straight line through 0 point. This is the third method to indicate the nonlinearity. Repeatability. The term repeatability and reproducibility of a transducer are used to describe its ability to give same output for repeated application of same input value. So input doesn't change, you are giving the same input value again and again, and the capability of the instrument to reproduce the same output again and again for the input, then it has good repeatability or reproducibility. And this can be calculated maximum minus minimum values given by full range into 100. Stability. Here the stability of a transducer is its ability to give same output when used to measure a constant input over a period of time. So here this term is very important, over a period of time for constant input. For example, measuring flow rate for a period of time, that is the stability. If there is no stability in the measurement, then it is having drift. It is having the drift. The antonym for stability is drift. Then we have dead band or dead time. So the dead band or dead space of a transducer is the range of input values for which there is no output. So you are giving input but still there is no output observed. So that is that band of input values are known as dead band. And resolution, as we discussed earlier, the resolution is the smallest change in the input values that will produce an observable change in output. So that is the resolution. And you might be clear with that graph step diagram, right? You might have understood what is the difference between the sensitivity and resolution. Output impedance. When a sensor giving an electrical output is interfaced with an electronic circuit, it is necessary to know output impedance. Output impedance is the amount of resistance when you insert a sensor in the circuit diagram in the circuit. So that will cause some impedance in the circuit. So that should be taken care and that should be measured. And this impedance is being connected in either series or parallel with that circuit. The inclusion of sensor can thus significantly modify the behavior of the system to which it is connected. So these are the specifications of strain gauge. So range 72,000 kilopascal, or it is 2000 to 70,000 kilopascal. So supply voltage, thermal zero shift. We have full range output, that is for 40 millivolts. Nonlinearity hysteresis plus or minus zero point 0.5 full range output. So this is how the sensor is specified. Drift drift is the stability. If there is no stability, then the instrument is said to be having drift is a variation in the instrument output which is not caused by any change of input. It may be caused by internal temperature changes or component instability. There might be many reasons for causing drift. So the drift is gradual shift of instrument indication. Many environmental factors are cause of drift, such as stray electric and magnetic field, temperature changes, change in atomic structure, mechanical vibration, wear and tear, corrosion, aging components. The drift becomes significant when an instrument is used for a long time. So zero drift in the change in output from its set zero value over a period of time instrument calibrated may gradually shift by same amount. Threshold is suppose an instrument is at zero position, there is no input to it. If now an input is gradually applied to it, the instrument will require some minimum value of input before it shows any output. So this is minimum value of input after which it starts responding. So after receiving the minimum value of input, then the instrument starts responding. That is, it is producing output, observable output. So that is threshold. The minimum input which is necessary to activate an instrument to produce an output is termed as threshold. And dynamic characteristics here, if a measuring device is used for measuring any rapidly varying quantity, the relation between output and input is different than in case of static inputs. So here the inputs are in dynamic nature. This is called dynamic response of the system. The dynamic response of the system can be expressed by differential equations, zero order, first order, second order, etc. Up to second order, it is easy to solve. The dynamic characteristics of a device depends on the order of the differential equations. When it is linear differential equation, the device is dynamically linear. First order instrument, this is the characteristic equation tau y dot plus y equal to x of t, where x of t is time function of input, y is output of system. Lower time constant represents fast response and minimum error. So lower time constant is desirable, and it represents faster response and minimum error. So that is the time constant advantage when it is minimum. Second order instrument is characterized by two constants: natural response omega n and a damping ratio eta of the instrument. The second order system is represented by 1 by omega n square y double dot plus 2 eta by omega n y dot plus y equal to x of t. Omega n is expressed in radians per second, and eta is non-dimensional quantity. This indicates the relative stability of the system. So this is second order instrument. So based on this, we can have the two types of systems. One is poorly damped system or a highly damped system. Types of inputs, there are five types. One is step input, ramp input, impulse input, parabolic input, sinusoidal input. Step input is just like switch. So you are just switching on it, and the output will keep on existing. Ramp input, gradually increasing input is ramp input. Impulse input is pulse input. Parabolic input, the input is in the form of parabolic curve, whereas sinusoidal input is a alternate curve. So it is like AC supply. Then we have characteristics. First one is response time. You can see in this graph the response time. The first one is response time. Here 95%, this is 95% of input required to produce 95 percentage of steady state output. So this is response time up to 95 percentage steady state output response time, the time taken to produce 95 percentage of steady state output. So that is response time. Next, same graph you can see here. In the same graph, the time constant is 63.2 percentage of response time from the same graph. And this time constant is like measure of inertia of the sensor, and so how fast it will react to the changes in its input. So rise time, it is the time taken to reach 90 or 95 percentage of steady state value. So that is the rise time from zero to 90 or 95 percentage of steady state value, the time consumed to reach that percentage of steady state value, that is known as rise time. And settling time, it is the time taken for the output to settle to within some percentage, example 2% of the steady state value. So here within 2 percentage, the steady state value 55 degree centigrade, and so since 95 percentage of 55 is 52.25 centigrade degree centigrade, the 95% response time is about 228 seconds. So fidelity is like the stability in terms of static characteristics. Fidelity is the ability to produce changes in input signal faithfully. It is defined as the degree to which an instrument indicates the changes in the measured variable without dynamic error. So poor fidelity indicates non-linearity of measuring device or instrument. So lag, the delay in response of a device for a change in input, is called as lag. Every measuring device has some definite lag. So because of lag, the output response along with the time axis may be delayed. So these are the textbooks, and these are the e-resources. These are the static and dynamic characteristics of our sensors. Now we have completed the second topic, and we have other topics to discuss. In next session, we will discuss about errors, classification of errors, and error analysis. Thank you, students.